Today we're going to look at transformations. This year we're going to look at 4 types of transformations, 3 of which create congruent figures, 1 of which creates a similar figure. So today we're going to concentrate on the congruence transformations. There's actually 4 we're going to learn here today. The 4th, however, is a composite. It's just 2 of the congruence transformations put together. We have a little bit of vocabulary to look at, and then we can start looking at the transformations. The first thing is a transformation maps a pre-image onto an image. Every pre-image point has exactly 1 image point. All right, so what I mean by that, for example, with a reflection, if I was looking at myself in the mirror, I would be the pre-image, and my reflection would be the image. And every point on the pre-image has a point that matches to it on the image. A mapping is simply a one-to-one correspondence between the set of points of the 2 figures. So each point has a unique point. Each point in the pre-image has a unique point on the image. The pre-image is the original figure. The image is the transformed figure. And an isometry is a congruence transformation, and that's what we're going to be looking at. The first one, rotation. It's a transformation in which every point moves along a circular path around a fixed point. Circular path around a fixed point. Those are the 2 important concepts. It is a spin. When we are telling somebody to rotate an object, these are the instructions that we must include. We have to tell them about what point we are rotating, the number of degrees that we are rotating, and whether it is a clockwise or counterclockwise rotation. And there will be some pictures that I will talk about after we get through the notes. Translation. A translation is a transformation that shifts or moves every point the same distance and the same direction. It is a slide. The instructions we need to include are the direction in which we are sliding, up, down, left, right, north, south, east, west, whatever the problem is dealing with, and the number of units in each of these directions. A reflection. A reflection is a transformation in which every point is the same distance from the line of reflection or axis of symmetry. The line of reflection or axis of symmetry is also called the mirror. Everyday language, that's a flip or a mirror image. And the instructions that we have to give are over what line we are flipping or reflecting the object. The 4th transformation is a glide reflection, and it's just a composite of the translation and the reflection. And the reflection line must be parallel to the direction of the translation. And we'll see that as we work through some problems. The order of the 2 transformations is not important. So our instructions here would be a combination of translation and reflection. We would have to tell all of those things. Here's an example of a rotation. And now this is just notation. It's telling me take triangle ABC, transform, that arrow just means transform, and here are the instructions. I'm going to go 90 degrees clockwise about the origin. And this is the notation I used to say that this is the image, this is the pre-image. So A prime, B prime, C prime is the image point of each of these. So this whole shape is now transformed into this new triangle. We can't call this new triangle ABC, but we do like to indicate that it is a transformation, so there is a connection between these points. They're all shifted the same way. And you can see our clockwise rotation. And A moves 90 degrees, it ends up here. C moves 90 degrees, ends up here, and it's called C prime. B moves 90 degrees, B prime. That's our pre-image, our object, our original shape, and this is our image. And this is the point about which we are rotating. This is our reflection, and here you can see that each point, it's a little cluttered here, but this is our original shape here because there's no primes. So this is our pre-image. This point U is the same distance from the line, from the mirror, as this point here. They are equidistant, and this just means perpendicular. When we talk about distance, we have to look at perpendicular distance. If any random point on UT, it is the same distance as U prime T prime, any point on U prime T prime. So each one of these points, point S here is the same distance as S prime from our mirror. And notice our mirror doesn't have to be horizontal, vertical, it can be any line in space. This is our translation. Now just be very careful. Take a second and look at these two figures. Which one is our image and which one is our pre-image? If you look here, because this has no primes here, this is our pre-image. This is our original object, which we are moving this way. A lot of students just go left to right. You have to look at the notation. So this is the pre-image, this is the image. The figure here slides to the left 7 and down 3. And so again, here's our notation, similar to what we did with triangles. We have quadrilateral A, B, C, D, and this is going to be transformed. And this notation here indicates that I'm moving the x's 7 in the negative direction, I'm moving the y's 3 in the negative direction. So just like an ordered pair XY with parentheses around it, this is our transformation here for our translation. And we're going to look at those in class. And then these are pictures of glide translations. We have our mirror, our line of reflection, and this is triangle ABC. It is flipped, reflected about our line, and then it is translated up to here. This becomes our image. This was our pre-image, this is our image. We can tell it's our image because it has the primes there. A little hard to see, but there are primes right there. Another way of describing a translation is by calling it a vector, and we'll talk a little bit about that in class. The classic glide translation is footprints. They reflect, slide, reflect, slide, reflect, slide. And so when you think of a glide translation, this is the thing that you should be thinking about. The last thing I want to talk about is symmetry. Students often struggle with the question of symmetry. It's a vague question. If I ask you if something is symmetric, you could ask me, do you mean line symmetry or point symmetry? Do you mean reflectional symmetry or rotational symmetry? So sometimes when you ask a question, is there any line of symmetry, students see reflection or rotational symmetry, and it does get confusing. So I just want to take a minute here and talk about symmetry, although what we're going to concentrate on in class are the transformations. All right, so symmetry can be defined as the correspondence in shape, size, position, and we have two types of symmetry. line symmetry or reflectional symmetry. And that is the one that we tend to think about. Lines or reflectional symmetry has to do with folding an object so that the two halves match up exactly. The other type of symmetry is point symmetry, also called rotational symmetry. And certain objects can be spun around a point, and then they will line up exactly with the original shape. So let's take a look at these two questions here. I'm going to try to zoom in. All right. So let's look at the letter H here. I could fold H along a vertical line, and one half would line up on the other, right on top of the other half. I could fold along this horizontal line here, and the bottom would line up on top of the top. I could spin this right around this center point here, and the H would look identical to itself. With A, you can see your line of symmetry. It has a vertical line of symmetry, but it has no horizontal line of symmetry. It has no point symmetry. If I rotate the A 180 degrees, literally turning my paper upside down, it no longer looks like an A, it looks like an upside down A. N. If I fold N here, it does not fold on top of itself, so it has no vertical line of symmetry. If I fold it this way, it has no vertical line of symmetry. However, if I look at a point right there in the middle, and I were to spin this upside down, my N would look exactly like itself. So there's our answer, C. It has point symmetry, but no line of symmetry. E, of course, has a horizontal line of symmetry. It has no point symmetry. If I would spin this around 90 degrees or 180 degrees, it would look like an upside down or a fallen over E. All right, the next one. Which of the following has line symmetry but does not have rotational symmetry? Well, if I take this triangle and I rotate it, and I'm rotating it actually 120 degrees, it looks like a triangle. It looks to be the same way that it was here. This has line symmetry right here. It has line symmetry here, and it has line symmetry there. The square, if I rotate this 90 degrees, it looks like the square. It has line symmetry, it has line symmetry. If I take my trapezoid and I rotate it 90 degrees or 180 degrees, it does not look correct. Okay, so my trapezoid has no point symmetry. It does, however, have line symmetry. So there's my answer. Hexagon, I have lots of line symmetry. I also have lots of point symmetry. All I have to do is rotate it 60 degrees and it looks like itself again. Okay, so the answer to both of these two questions was C. Tomorrow we'll be working in groups on transformations.